So hello. Okay, so this week we will be interested in not anymore in single species populations, but interaction between different species. So let's talk a little bit about this. So first, our first approaches, we will look at interactions in pairwise interactions, so interaction between two. Okay? This is but everybody takes for granted that theory should be built by looking interactions between two, and then you can form networks of interactions, whatever interactions you are talking between a lot of species. So to study large communities or of species or large networks of species, you should start with studying the pairwise interaction between two. So that's the common law, and it's actually what is the main way of building the classical ecological theory. And just to mention that this is not the end of the story. There could be something called higher order interactions. That higher order interaction would be things that only happen if you say you have three. If you have two, they don't interact, but in the presence of three, all of the three interact. So it's it would not be an interaction this is pairwise. This would be a kind of what physicists call three-body. And and this is seldom present in theoretical studies, but some instances, like in vegetation dynamics and competition between actually trees, then sometimes this has been invoked. Okay, so this is just a disclaimer that it's not the only thing that we can do is to study pairwise interactions. Okay, so now let's think about what's our interactions. Okay, so this word has a kind of common sense. Maybe I would like to know from you, when I talk about interaction between species, what does it sound like, or what can you give me examples of interaction between species? So predation, which is the consumption of a individual of a species that is called the prey species by the predators. Okay? More. Parasitism. Yeah, parasitism is also an interaction. So you have. I don't understand. Symbiosis, yes. Yeah, you have symbiotic interactions. That word is used more in the context of when you have, for instance, certain. It's more used in the context of endosymbiosis, which is when you have say, for instance, bacteria that you need to have and for digestion. So there you have you give them habitat, and then they give you back some better functioning of your body. So this is symbiosis. Then when it's more like most of the time we speak more about mutualism, which is not so much connected. You have this kind of endosymbiotic things. It would be like plant pollinator, for instance. Plant pollinator is a classical example of mutualism. So plant gives nutrients for the pollinator, and the pollinator helps the plant to reproduce. So everybody gets just fine. So more things, more interactions. Interference. Yeah. Well, yeah, interference. But so interference is a way, but usually interference would be connected to there's some reason to have interference, right? So interference is something that we actually want to discuss in the context of competition, okay? So more ideas. Commensalism. Commensalism, I'm always make confusion between amensalism and commensalism. Commensalism, if I'm not wrong, is a neutral for one species and positive for the other species. So that's a kind of thing that happens, for instance, if you have a big mammal and the mammal can carry some insects or that live on that mammal, but these insects do not harm the big individual, and then he makes the transportation, and therefore, well he has no gain, but one of the species, the small insects or whatever, have some positive effect because they have been transported to places where they can reproduce easier. No, more.
It's not an example, it's a question. I was thinking about like artificial selection from made by humans to their domesticated species, and then the coevolution processes on mutualism, and maybe you could just talk a little bit about it, like the parallels and the similarities too between those processes, like coevolution by artificial selection and coevolution by mutualism.
So okay, so just to make it clear, this is sure. We are talking first of ecological interactions, which may shape or not evolutionary processes, so by natural selection. Okay, so all of the interactions that we spoke, for instance, mutualism, predator-prey relations, and so on, they can have if long-term effects on which may have to do with natural selection. Okay, all of them actually. So then there are, if you want, a predator-prey relation can shape typically an evolutionary process. For instance, there are heterogeneities, say, in both the predator and in the prey population. So maybe some individuals from the prey populations are much more difficult to be preyed upon. So this could lead to a kind of selection process in the prey population that certainly get easier away from the predator, and the ones that don't, they have some trait that is being selected negatively. Okay, that can happen. And then you can also have heterogeneities in the predator. Maybe there are individuals in the predator species which could be much more efficient than others, and eventually the weaker guys don't have access to enough nutrients, and then you have a selection process that can, and then you can have always this kind of thing. Both of them are selecting each of the one to the other. Yeah.
So just to clarify my question, what I had in mind were like more, I don't know, exclusive relationships between like pollinators and some plants, or some more not so generalistic. No, not the prey, the predator. And like thinking of on the perspective of models, if we're trying to think about, I don't know, corn and humans. Like corn wouldn't survive without humans. It needs to be planted. It's not a kind of plant that has a lot of ability to colonize places on its own. And then I was thinking of the parallels that it has with those more exclusive mutualistic relationship between other types of animals and this coevolution process maybe. And how to like model it if you like, for example, let's say I want to understand how corn or coffee will react to the climate change, and how would I try to model that, and if it would have any parallel to how would I try to model some pollinator plant interaction.
So, from the modeling point of view, for instance, let's go back to corn and humans, for instance. So that's a consumer resource-consumer relation, which we could assimilate to predation. So I will explain exactly what predation, the meaning of the word predation that we will use, that most books also use. But so that's a consumer resource relation. And obviously, then there could be this kind of thing that you have. These species interact certainly, right? And the interaction may shape the evolutionary history of many of corn in this case. Right? So, in order to model this, you would have to have a modeling framework where you have the species, and the species have traits, and then the interaction may change not only the population size, but also the proportion of certain traits. So usually this is called, most of the time it's called adaptive dynamics. And then in order to model this, you have to say, the easiest thing is when traits can be counted. So trait 1 and trait 2, not a continuum, but usually it's a continuum. Let's say then you take your population with trait 1 and call it N1, and your population, which is the same population, therefore they can interbreed and so on. But you call N2, and then you have two populations from the same species but with different traits. And this is the modeling framework for this kind of things. Right? We won't work with this because evolutionary biology is not part of the map. Maybe, I don't know, in the advanced part we will have something. Okay. So now let me come back to all the things that you have mentioned. There are many possible interactions at the level of the individuals. For instance, one that was not mentioned explicitly, which is a host-parasitoid interactions. Post-parasitoid, you have a host. This is usually things happening between insects, okay? And have a host, and then you have the parasitoid which attacks the host but doesn't kill the host. Just lays eggs usually on the body of the host, and then these eggs over time will hatch and kill the host, and then there will emerge a new generation or new individuals of the parasitoid. So, for instance, this is different when you say from predator-prey. Predator-prey seems to be something different, right? This is just the consumption of one in benefit of the other, right? So, but now let us think that we are talking about population biology. Okay? Population biology. Not only, we don't want only to characterize things that happen at the individual level, but how population sizes are affected by interactions that happen at a certain level. But so we can have a view of the categories. Okay? So say you have the species A and species B. And then you have an interaction, say, here, say the interaction is such that it is positive for A. So positive means the population tends to increase due to the interaction. This. And it's negative for the other one. Negative means the population tends to decrease. So this clearly includes predator-prey, host parasitoid, and maybe others that you can imagine. So this is sometimes called antagonistic interaction and so on. But well, we will call it predator-prey. Because it's usual to call it like this. But you have to have in mind that this is a kind of generalized predator-prey that could also be host parasitoid and other kinds of interactions which are positive, negative. Okay? So not to confuse necessarily with exactly predator-prey stricto sensu. So then you could have interactions that are negative for one, negative for the other one. So it's mutually negative, and that's called competition. And then you have the last case would be plus, which will be called mutualism. Well, and then you could go on putting 0 plus, 0 minus, and 0, 0, which would be neutralism, which is something that has no effect on the population. So, but we won't go into this. We will be happy with these three. Now, today's class will be about competition. And so, tell me what you think about competition. So, how do species compete? They what?
Sometimes they might need the same resources, so even though there's not a direct confrontation, they.
Yeah, exactly. This is exactly about something which is an important point, which when we talk about species interaction, just a minute, species interaction at the level of populations, maybe there's no interaction at all at the level of individuals. It's just that they are exploiting the same resource. Okay? So this is also called an interaction, but an interaction at the level of populations. Okay? It's different, for instance, from predator-prey. Predator-prey, actually there is an act of preying in predating and so on. But competition can have this kind of thing that the competition could be just completely exploitative of a resource, and therefore if one individual feeds on the resource, others can't feed on the same thing, and therefore there's negative interactions. Okay, yeah, who has the mic? No, okay.
Just something I wanted to ask. When we say competition, do we say constant competition, or are we also talking about a competition that happens in a period of time? For instance, territoriality. For instance, one species considers a certain area its territory, and another species tries to take it away from it. Could be a certain type of competition for territory, but it happens temporarily because one species eventually leaves.
So, okay. So two things. First, I'm glad you mentioned that territoriality, which is an example of which is not called usually exploitative competition. That's called usually either contest competition or interference competition. Okay? So actually, there exists such a thing as interference competition, which is very usual, for instance, with birds, with songbirds usually, that actively, the individual actively tries to avoid the presence of another species. Just goes there and interferes with him. Okay? So that's a way of competing, because it's not predator-prey, because it's not consuming the guy. It's just kicking it out of his territory. So that's a way of that's a very important way of competing. And well, competition could be variable in time. Maybe maybe certain interactions, but not only competition, there are many others, could be connected to seasons or environmental fluctuations. So the interactions may be context dependent, and if the context goes on changing, then you can also have variability in the population. And it can also be variable along the life history of individuals. There's a famous story about the cactus and a certain tree in American desert of Sonoma. And so I think the tree gives shadow for the small individuals of the cactus species, which is a kind of nursing interaction. So it's in principle it's commensalism in the sense that no big advantage for the tree, but certainly for the cactus. So that it begins with commensalism, and then when the cactus grows, it adds to kill the tree. So it kills the tree. Therefore, it is antagonistic. Okay? So over the life history of this species, of the individuals, the interaction between these two species changes depending on the age of the cactus individuals. Right? So it can be changing. Yeah. Phone, mic. Yeah. Go hard.
When I said interference, when you ask about relationship between two species, I was thinking about the relation, one kind of relation, like human fish.
Human
and fish. When we produce some kind of waste and put this waste on a river, I don't see how this is a minus relationship, because I don't see how this affect in a short time the human population, and this is kind of a question, because how do I classify this relationship? And the second one, it's considering time on it. How do I model? Because in short time, this could not affect the relationship, the human population. But in the long time, with considering other relationships of the fish and the environment and the other species, this could affect...
kind of backfire the human.
Yeah, exactly. Yeah. So how do I consider all of this in a model?
So what you you have to have different models for different time scales. Remember that we discussed this last week, that models assume a certain typical time. Remember when we talked about the population of the Europe in the 14th to the 17th century, and then you had the bumps, but if you look this on a very long time scale, it was just disappeared, the bump. So, for instance, just polluting rivers that affect the population of fish in the short time would be amensalism. It's negative for the fish, but the humans, it could be marginally positive for the human species in the sense that they have to, the waste has to go somewhere, but could be also something else. So it's between amensalism and antagonistic, but more or less, okay? On the long time scale, then you have something else, and you have to model all the processes that are important on a time scale, say, of a century. So the pollution thing is an year, 2, 3 process. If I want processes that are important on centuries, then you will have to have a much more complete model, right? And then you have to first know what are the processes that are actually important on the level of centuries, okay? So you could say there could be a cascade of effects. It starts with certain fishes, but then the humans were not the only consumers of the fishes, there were other species, and so on, and so on, and so on, and so on. And then you have this kind of trophic things. So one example, it's not exactly the same, it's a little bit even at the contrary, but it's very illustrative, which is an ecological disaster that happened in Lake Victoria in Africa. I think this is Tanzania. And, well, it's a very poor region, and there were fishers, and the lake didn't have so much good fish. So some people thought, okay, we just bring in new fish species, which will be easy to fish, and is big and a lot of nutrients and so on, which is a perch. Okay. So they then took it from the Nile perch, and put it in the lake. Okay. Complete disaster, because the perch dominated completely the lake, completely. And other species started to disappear, but other species also have interactions which had to do things that happen outside the lake. And at a certain point, there was even kind of starting of a near-shore desertification process, because of a series of interactions that had been modified by the presence of the perch. So this is a reminder that there is no such thing as ecological engineering, okay? It usually ends in disasters. So, why? Because it's a complex system that you cannot model all the aspects. Because, for instance, with the story of Lake Victoria, the desertification process has to do with some nutrients in the soil that were affected by some bacteria, which were connected to some fish, and the fish disappeared, the bacteria disappeared, and everything went away. But you could not have this mapped so completely in order to know exactly what will happen. So there's no such thing as an ecological engineering of an not an ecosystem, but maybe a community or network of interactions. They are always very, 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 very large and difficult to find the parameters and so on. So, okay, let's go back to competition. And at the level of the effects on the population, we can just consider only competition and basta. not necessarily differentiate interference from exploitative. And because actually the interference, although being different biologically from the exploitative, also has the same effect. That for instance, a territorial bird is just getting guarantees that it will have nutrients, and the other one is not accessing it. So it's not by exploitation, but the effect on is negative anyhow. Okay, so that's why we can put in the first model, we can put these things together. So there are two different biological concepts at the level of the individuals, but they get unified as negative interaction with, and we call this competition. Okay? So, okay. Now, where's the... And we will still predator-prey, if not tomorrow, maybe the day after tomorrow. So let's start with this one. Now, yeah, there is some context about competition that comes from the 19th century, before even any mathematical biology existed, even no models, and so on. But it dates back to something that is sometimes not made explicit in the 19th century, but there is the idea that species that have similar resources rarely coexist in the same place. So this is not explicitly stated, but this permeates Darwin way of thinking, because it actually, what is behind this, the competition is a way of natural selection, and natural selection drives evolution, and so on, so on, so on. Okay, so somehow the competition concept was already kind of present, and the effect of competition has been already discussed before we have a theory. So explicitly, if you want, Grinnell, which is a very important guy in the story of ecology, in 1904, says that two species with approximately the same food necessities rarely will remain in their population size, balanced population sizes in the same region. At the end, one species will eliminate the other. So that's 1904. 1904, there was no theory about this. There was a verbal theory. So it's an interesting thing. Interplay between what we discussed on Friday and so on, about how theory is formulated in ecology. You can have conceptual theory without the math. But then you will also see that with the math, we will make it more rigorous, and we will give steps and ask new questions. Okay? But so, Grinnell had already this idea clearly stated. And this, all of this, from the experimental or observational point of view, it more or less gets a kind of synthesis in the work of Gause, which if you probably remember from the first talk of Paulo Inácio, and then we mentioned this guy many times in the Soviet Union. This book called The Struggle for Existence, and he has there's a statement that says that two species with the same ecological interactions do not coexist. That's called the principle of competitive exclusion. Right? So it's stated as a principle by Gause. Right? Two species which have the same say nutrients or resources, they do not coexist. That's the principle of competitive exclusion stated by Gause, and it's obviously not true always. So it's kind of an elementary process, but when you say, no, guys, here these species are very similar and there's a certain coexistence, then you will have to explain why the coexistence is. Maybe one of them has certain advantages and over the other, but the other that would be weaker maybe has some other kind of behavior that allows it to differentiate a little bit from the other and then therefore coexist. So this is the idea, and this is an idea which is essentially what's behind of this, all of this is that that competition could shape this kind of situation. Competition would be a driving force of which species exist in a certain place and which species are eliminated by the presence of others. Okay? So which would also, taken to a longer time scale, have a natural selection process effects on the natural selection processes. So now this has been stated as a principle, but Gause is, I think, 32 or 34, 1934, book of Gause, and before we have already had some models for interaction species. So the first model for interaction of species which are important for modern science. And the models written down by Lotka and Volterra. Which we will study. There is something called the Lotka-Volterra model for predator-prey interaction, and then there's also the competitive Lotka-Volterra model. This is the one that we will write down today. Right? So just for some context, Volterra was a very important mathematician in Italy, and he was one of those guys that lost his professorship because he opposed fascism. And then there's a curious story about him connected to the Lotka-Volterra equations for predation, but I will tell this story just when we talk about predator-prey dynamics. And Lotka is also a fascinating guy because he was born in I think it was still Imperial Russia, but then today would be Ukraine, but of American parents. And then he moved to study at the university. He moved to Scotland and then studied in Scotland. And there he started his academic life as a student, and actually for the physicists here, he has been a student of a guy that sometimes we forget the existence, but he's always in the electromagnetism courses, which was Poynting. So, but then he moved for a PhD in Germany, and Now the name of the German guy, Ostwald, which is a guy, maybe I've heard Ostwald. Ostwald was a guy from chemical physics. And he was very important in establishing the law of mass action between reactions between different chemical species. And Lotka worked with him, and then they had the idea that maybe species which are not chemical, but species that are biological, could be modeled in a certain way which is similar to the interaction between chemical components. And that's what he did, and he didn't write a paper, he wrote a book, okay, which was called, I think, physical biology or something like it. It's not called mathematical biology. And then he moved to US and actually worked with Raymond Pearl, with already some person that we already mentioned here. So he worked with Raymond Pearl and never got a position. Never got a position. But he was really good with statistics, and he actually got rich doing statistics for actuarial and financial things. He even became the president of the Statistical Society of America even, okay, although he did not have a position. So it's not the only thing in the world that can make you happy to have a position. You can also do something else. Okay, so now for the math. So what's the rationale behind Lotka-Volterra? It's that we have two species. You have to have two functions, one for the species, one species, and other for the other species. And so we will count the population sizes of two species. Now, interactions mean that one species has an effect on the other. Okay? So our first assumption is that in the absence of any of them, in the absence of the species, each of them, when they are not in interaction, each of them would have a logistic growth. Okay? So we would write down dn1 et would be like there's a certain R1, and I want to write this in this way, K1, which is a carrying capacity for the species in the absence of the other species, and I write K1 minus N1. Okay? So that's the logistic growth, okay? Because it divides here, that's 1 minus N1 over K1, okay? It's the same thing from the last class. I'm writing this way because it will be will be easier to generalize to interacting species. So now, the second species has also, they have different intrinsic growth rates, and they have different carrying capacities. These are non-interacting. N2 has no effect on N1, and N1 has no effect on N2. So how can we make them, how can we write down a way of making them interacting is just saying that N2, the presence of the population index 2, has a negative effect on the rate of change in time of the population N1, which is easier to model, just writing some proportionality constant. Here. Yeah? There's the mic.
I didn't understand. Like this equation we've already seen, right? It's the same that we've seen last week. Okay. Then N1, it's just the population without competition.
So N1 and N2 will be, we want to build a model for two competing species, which I call 1 and 2. Okay? The two species that compete. So, in order to build the model, I consider the situation that when there is no competition, I just segregate one of them. This is not present. Okay? Say population 2 is not present, and in this case, the population just grows of species 1 grows logistically to a certain carrying capacity, which is K1.
Oh, okay. So I was taking coffee. These are two different species.
Yeah, these are two different species. They are the competing species. So, and in order to simulate the effect of species 1 on species 2, I will do the same thing, but I put a different coefficient, which I will call beta, because we like Greek parameters. So, now, think about what are alpha and beta? Alpha and beta are, again, phenomenological parameters. There's a question, and where's the mic? The mic. Oh, okay, you have already a mic.
I'm just trying to understand one thing. It's based on Malthus law, right?
It's
based on Malthus law,
logistic
right?
law.
Yeah. If one of the species is not there, then it grows exponentially.
No.
No?
Logistically.
Oh, logistically.
Logistically.
Oh, I heard it wrong then.
Okay.
Sorry.
Okay, logistically.
Maybe it's missing N1 on the outside.
Ah, yes, I'm missing N1 and N2. Yeah. Oh, thank you. Now it's really logistical. Okay, sorry. I forgot this one. Okay, so now alpha and beta are again phenomenological parameters because we are not describing the actual things that are happening. For instance, if it's consumer, how the resource is being consumed at a certain rate. We are just saying that somehow species 1 is detrimental for species 2, and species 2 is detrimental for species 1, and that's it. We have not tried to model the actual way it's interacting, which we will do next week. It's just called modern competition theory. It's just consumer resource dynamics. But now, for time being, that's it. And then alpha, you can think alpha, say alpha is equal to, say, 4. It means that the effect of one individual of N2 has 4 times the effect of the individual of N1 on the species N1. Or if alpha is 0.5, means that the effect of N2 is for an individual of N2 has the same effect as half of N1. Okay, so when alpha or beta are bigger than 1, we say that the system is dominated by interspecific competition, and if alpha and beta are smaller than 1, then we say competition is dominated by intraspecific competition between the same species, and if one is bigger than 1 and the other one is smaller, it's a kind of mixed situation. Okay, so now here we are. We have the equations. Now, this is the first example of a mathematical object that's called a system of differential equations. In the case, 2 differential equations. Okay? There's no sense of saying I want to solve the first one, because the first one has N2 here. Therefore, you would have to solve this one, but this one cannot be solved without knowing N1. Therefore, the system has both equations have to be solved at the same time. Okay, so that's a system of differential equations. we cannot solve. But so you can ask Renato to solve on the computer for you. But you know, this will be messy. Why? We have so many different constants here, or the parameters. So you expect, for instance, if you believe in Gauss, you expect no coexistence, but certainly that can not be completely true for these equations, because if alpha and beta are very close to 0, then you could pose the question, will it take an infinite time to eliminate the other one, or maybe they can coexist? So okay, that's a question. Okay. Then say one species excludes or eliminates the other one, but surely for different values of alpha and beta, that could be species 1 and species 2, and then you would have to numerically, with the numerical procedures for differential. Has Renato already talked about solving differential equations, or is it still on the syntax part? Not yet. Okay, he will. There's a question there. The Mike. Okay, that's already there.
I would like to know, in the case of more than 2 species, are we going to use the same equation? If the answer is yes, in this case, maybe we are going to add the third species, N3, and the parameter maybe lambda. What will be the interpretation of this parameter?
Okay, so first of all, you could say we want more species, and actually we will discuss this, not now. Okay, we will discuss 3 species interactions in the next weeks come. And for instance, you could have a third one here, and then you have to make hypotheses about your interactions. The most common hypothesis on the interaction is that they are pairwise. Therefore, if I add something with a 3 here, then you would also maybe have more terms on all the sides. It's getting lots of parameters. And then you would have one here, but you would always say the interactions are pairwise, which means that the terms that come in an equation is like, you see, n1 times n2, and n2 times n1. If you had a third species, there are two possibilities. We could say, okay, n1 and n3, and n1, n2 and with n3, and n1 with n3, which does not modify the rest, but it could also modify. So in which case you would not have a pairwise interaction, which is much more complicated, and it's not so general in nature. So I mean, it's not so happening all the time. So we won't do this. Okay?
In this case, we are going to fix some individual whenever we are doing
the parameters. Yeah. So this is a point here which is difficult with these models. That's because they are phenomenological. Okay? So we cannot expect to get much out of it in a strict way, in the same sense that we discussed the logistic equation. The logistic equation has a phenomenological parameter which is k. It cannot be measured at the level of individuals only. It's not like predator-prey. Predator-prey, you have attack rates of the predator. You can go and look at this and then say, at the level of population, this has had an effect. K is only defined for the population. And the same thing is alpha and beta. They are only defined for the population because they are not doing an upscaling of individual characteristics. So that brings us to the hell of parameters, which is a very, very hot hell. in all kind of models, not only this ones. Like for instance, it's very important for epidemiological models and so on. There are sometimes many parameters that are unknown. You don't have the value. And then you say, God, but what do I do? So most of the time, when you have larger sets of equations, you will have to give a value for the parameters based on previous knowledge. Sometimes you know maybe not the value, but you know the range. It's between 5 and 10. Okay. You go and just put a 7 there. And then at the end, you see if the result is very dependent on this. It's called sensitivity analysis. And then you can also say, well, okay, I can use them to fit the model. The unknown parameter, you have seen fitting with Paolo and Andrea, I think, a little bit, yes? And just a minute. And you can use the unknown parameters to fit the model to your data. And this is dangerous also. Say. Better with the mic because.
Is that unsolvable?
Unsolvable.
Or is that solvable?
So it depends on what we mean by solution. Okay, there is a solution.
So when you said like in the computer, is it solvable or not solvable?
So it is not analytically solvable. Analytically means that you can write down an expression for the solution with all dependence of alpha, which has explicit dependence of alpha, beta, k's, and r's. So this is not possible for this equation. So, but doesn't mean there is no solution. Okay, there's a solution, but you cannot write it down in terms of known functions. And remember the discussion at the beginning. Known functions is a problem of human beings, not of mathematics. Okay. So there's no explicit solution. Okay? So there are always two ways. One way is numerically explore this numerically, and the other one is qualitative analysis, which we will do right now. Okay? So no explicit solution.
Second thing was, what did you call hot hell?
Hmm?
What did you say was a hot hell?
Hot hell. The hell is the following. So maybe you have some data about some system, and you have a model, okay? But a little bit more complicated model, okay? It would be a lot of parameters. So a lot of parameters, and maybe you don't know the value of the parameters. So what do people do? So most of the time you have the model and you want to see if the data correspond to the model, but you don't have the parameters, and say, okay, as I have no idea about the parameters, of certain parameters, I can just adjust the model, fitting the model to the data, which I think Paolo explained and Andrea explained at the very beginning with the logistic and so on. You can fit it. Now the problem of fitting is overfitting. I don't know if Paolo or Andrea have talked about overfitting. No, but overfitting is a hell. Why? Because too many parameters can fit anything. Okay? If you have 10 free parameters to fit a curve, nice, fits completely, but has no meaning whatsoever, because you are overfitting. That's typically what happens. For instance, let's go back to the example of Andrea with the regression. You have some y and some x, yes, and there are some points here. Okay, so you can also fit things like this, or you can fit the equations that should explain this. But here she discussed just a statistical model, not a mathematical model, but you also can think about mathematical models. And then say, let's do a linear regression and find the best curve that gives you the minimum sum of squares of residuals. So that's life. Okay. Then I say, okay, How many parameters has a straight line? 2. Okay? Now say you have some more points here. Okay. Say that you have fitted only this part. Only this one. And then you want to predict this one. Because, you know, predicting things in the future is good business since ages. If you predict future, you are rich. Okay? And mainly in finance, you have to predict the future in order to do your investments. And that actually, in finance, people don't have to be very good with models, actually. Because if they are right 51% of time, they are already making profit. Okay? We scientists, we want 95% confidence intervals. We want to be only wrong 5%. They admit that 49 is already good for them. Okay? So you would like to maybe to go this one. Then there comes a guy that thinks he is smart and say, I can do much better. Why a line? I can here, how many points I have? 1, 2, 3, 4, 5, 6 points. With a polynomial of order 5, I have 6 parameters. And I can just find, will be a lot of calculations, but I can just find the parameters that make the curve do exactly this. Okay? That's a 5th order polynomial. And then you say, let's predict the future. Overfitting. So that's always a trade-off between prediction and fitting. So what's behind this kind of thing is that these points are actually not the result of a deterministic model. They are random variables, therefore they could be here or there also, okay? So that's why you try to make only with 2 parameters, okay? And then, well, there's all the ways of actually comparing the models and this ICTP tests and so on. So that's more statistical. But anyhow, when you work with models, this kind of model, what do you do with the model is usually, what we want to do also, is usually to extract the qualitative behavior. So we want to understand if this model can explain, is it consistent with competitive exclusion? Does it predict that we will have competitive exclusion? Okay? So that's the thing which is not connected to data. But when you do models, and not this one, or other models for species, interaction, and so on, and you have data, then you have the same kind of problem as here. If you have too many parameters, you can fit anything. Okay? And there is a famous joke by von Neumann, which is a very important mathematician. Worked, I mean, it's a German mathematician which in exile worked on Manhattan Project and stayed in Los Alamos there. And he was a very famous guy and so on. And then somebody came with a super overfitted thing and they said, well, give me 5 parameters and I can draw you an elephant. Give me 6 and I can make it, how to say, move the trompa. No, exactly. And you see, that's a general aspect of relations with data in models. It's overfitting is very, very dangerous. Okay? So
alpha and beta are phenomenological parameters.
yeah.
So in this case, there is any difference between alpha and R2?
And
In this case,
alpha and
R2, the growth rates of N2
the
is
R1
R2.
and R2.
There is what is the difference between R2 and alpha?
So R2 is the intrinsic growth rate, okay? So it's connected to birth and death rates in the absence of competition at all. And alpha is just the effect of the species 2 on the species 1. Okay? So, for instance, if alpha is equal to 1, the species 2 has the same effect as the species 1 on itself. If it's alpha is equal to 2, means that one individual of a species 2 has the same effect as 2 individuals of species 1, because the effect is here on how much they modify the increase rate or decrease rate, right? So this is the, right? So, okay, so we will come back to the stories about parameters and fitting over and over again, and I think probably Paolo and Renato also will talk about this. Okay, so Mike.
Kind of on the same topic of Moi's question, how exactly do we measure the species effects on another?
So that's the point. That's the point. It's phenomenological. So the point that it's phenomenological, it's, for instance, let us think about predator-prey first. Okay? So you can go and look at levels on individuals and see how many prey a certain consumer is able to consume over a certain period of time. You can go this. This will give you, in the predator-prey models, will give you the value of a parameter. Okay? So, but this was measured with individuals, looking at what they do. And at the level, for competition, that's not possible. Okay? Because we are not modeling the actual process of competition. We are just saying, I have population 1 and I have population 2, and they are detrimental. So how detrimental can be only ascertained after you run an experiment. Okay? So that's what actually Gause did. Gause worked with paramecia, which is microorganisms, and which is there's one is called caudatum, paramecia caudatum, the other is aurelia, and so he grew them separately and saw more or less population that stabilized at certain carrying capacity. So you could measure the carrying capacities before making them compete, and then it puts together in the same recipient, and they compete, and one of them eliminates the other. Okay, now. Then you say, okay, but can we explain exactly the values using this model? Then you would use alpha and beta, and you would find the values of alpha and beta after you have done the experiment. But you see, this is the problem with phenomenological things, because you may find it, but they were not, your model had made no prediction because you didn't know alpha and beta. Now, so it didn't make any prediction, but well, at the end you can calculate alpha and beta such that the model had given the correct prediction, but it's not predictive model in itself. What could happen is that, for instance, you could show that the model it's completely wrong in the sense that no alpha and beta will give you anything like the model. The model gives you different patterns. Maybe they oscillate or do something else, so that doesn't happen. So you can reject the model. Okay? If you have enough statistics to reject it against the, if you cannot, I mean, okay, if it goes completely wrong and you have a null hypothesis, which is much better. Okay? So that's it. So it's again phenomenological. So what we want to study is the pattern of coexistence and non-coexistence. We don't have time to do this all today because this involves considerations about stability of fixed points. And that will take some time. We will do this graphically, but let me first start the calculation that we will then finish tomorrow. Now, very nice. And so, if I don't resort to numerical calculations, I can try to find the general behavior of the functions that are solutions of this equation. And this goes, in this case, asking myself what are the values of n1 and n2 such that the population will not change. They will be in equilibrium. What are the values? Okay? These are called the fixed points. Okay? If this is 0 and this is 0, because we are supposing that at the fixed point they don't change, then you have R1 N1 times K1 minus N1 minus alpha N2 divided by K1 is equal to 0. R2 N2 K2 minus N2 minus beta N1 divided by K2 equal to 0. So, there are 4 fixed points. Let us write them down. So the first fixed point, and I will use this N1 star just to make it clear that these are the fixed points. It's not the arbitrary function. Okay? So the first one is N1 is equal to 0, which makes this equal to 0. And this one is also equal to 0. So the fixed point at the origin is a fixed point, okay? Which is what happens always. Because if you don't have the species, and one neither nor the species 2, then there's nothing happening. Okay? So it's a fixed point always. But now, so this is the fixed point I will call number 1. And then the fixed point number 2. So fixed point number 2, let's say that N1 is still 0. But N2 is not. Okay? Then this part has to be 0. But N1 is 0. Therefore, only if N2 is equal to K2, it is a fixed point. Okay? And you can verify. You put here N1 equal to 0, it's verified. You put it here, then you have K2 minus K2, which is 0, minus something which is already 0 because N1 was 0. Therefore, it's 0. Therefore, it's a solution to the equation. Okay? K2. Okay? And symmetrically, we could have N2, N1 equal to K1 and N2 equal to 0. Just you go here and say K1 minus K1 is 0, minus 0 is a 0, and N2 is 0, then this is also 0, therefore this is a solution. And then there's a fourth possibility, which is none of them is 0, and this parenthesis here is equal to 0, and this one is also equal to 0. As K1 and K2 are both positive, and they're constants, what I need is to solve this system of linear equations. Let me put here the stars. So this is a linear system, algebraic linear system that you can solve, and it's everybody knows how to solve this system. You just eliminate the right n1 in terms of n2, and then plug it in the other equation. You get an equation for only for n2. You solve it, and then you get back to n1. Okay, so I don't want to spend my time doing this algebra. And then you would have the solution of this would be n1 star is k1 minus alpha k2 over 1 minus beta times alpha, and n2 star is equal to k2 minus beta k1 divided by 1 minus beta times alpha. So, what do they represent? Yeah. Where is the mic? Oh, okay, long wait mic. Okay, it's already one.
Sorry, it's going a bit too fast for me. Could you go explain again the fixed points and go again through the fixed points each situation and explain to me what is the small.
The star?
Yes.
Star is just a way to remark that this is not n of t. That's a fixed value of n. It's the value at the fixed point. Okay. Okay. So what's the fixed point? Fixed point is when population don't change. They have constant population levels. Therefore, the derivatives are 0. Okay? The derivative being 0 means that this right-hand side here has also to be 0, which is written here. Okay? And then these are equations for n1 and n2. So 2 equations, two unknowns. You can solve it. And the first one is obvious when you can take n1 and n2 equal to 0, then this is verified, it's 0. It's also 0, that's this one. But then you look here and say, if I take n1 equal to 0 here, which makes this part equal to 0, I can, instead of taking n2 equal to 0, can make this part of the expression be 0. And this is when n2 is equal to k2. Because n2 is equal to k2, this is 0, and n1 has already been put equal to 0. Therefore, all of this is 0. Therefore, it's 0. And this is this equation, this point. 3 is this point. This is the same thing as before, just changing 1 per 2. And then there's the possibility that none of the populations is 0 at the fixed point. We say n1 and n2 are different from 0, therefore all of this part of the has to be 0, and this one has to be 0, which is expressed that here k1 minus n1 minus alpha n2 is equal to 0, k2 minus n2 minus beta n1, which is what here is equal to 0. And this is a system of linear algebraic equations. Okay? You can solve this by just, you say n1 is equal to k1 minus alpha n2, then you plug it here, and then you do some algebra, and you find the value of n1 and n2, which happen to be this ones. Okay? Now, so let's, again, lots of fixed points, but we already learned that fixed points that are unstable are not interesting. We want to know when fixed points are stable. We want to know, if I start with a given initial condition, if the dynamics goes to a fixed point, which of them will be attained? Okay? So all of this will be the next class. Okay? But for the time being, just let us and make an interpretation. This is absence of both species. Okay? The absence of both species is obviously always a fixed point, because you don't have either species that cannot appear any species from anywhere. This one means that species 1 was eliminated at the end. I mean, if you get to this point, n1 disappeared, and N2 is at the carrying capacity. N1 equal to K1 means the symmetrical case, N2 disappeared, and N1 got to the carrying capacity. And then you have this one, both of them are different from 0. That's coexistence. Okay? So, now, as is the case with, always the case with the population cannot be negative. Okay? So, one thing is, these things, depending on the values, could be negative. And therefore, the fixed point of does not exist for all values of K1, K2, alpha, beta. It only exists if this is positive. Okay? Say the numerator is positive. When you look here at the bottom, you have 1 minus alpha times beta. So alpha and beta were the coefficients measuring the force of the competition between both of them. And then surely if they are very small, alpha and beta are small, then supposing that the numerator is positive, then it's only if alpha times beta is smaller than 1 that this could happen in this case. Okay? Which would mean that the force of the interactions, okay, is somehow weak. Okay? This is kind of, I mean, because you could have one bigger than one and the other one so small that both of them would be still smaller than 1. Okay? But one situation where alpha and beta are smaller than 1, then there is the possibility of coexistence. And alpha and beta being smaller than 1 means that the effect of the competition, of the interspecific competition, is smaller than the effect of interspecific competition, because N2 has, say, alpha is small, and it means that N2 has no big effect on N1 because that coefficient is small. And the same thing for beta. Okay, so one possibility of the model is to have coexistence. Now, fixed points need to be analyzed in view of stability of the fixed points. Now, stability of the fixed points will be can be studied in 2 ways, which is actually only one. We will do this graphically, which can be done up to equations of order 2, because the solutions you can think N1 and N2 is a kind of axis of a space, and then you can look for the solution there. If you had 3, you would have some 3-dimensional things, and then you got lost completely. So then there is another way, which is doing this calculation in what's called an analytical way, but we don't want to do this here. If you are mathematically trained, it's very easy, but if you're not, what you have to do is you say that you are a fixed point and you make a perturbation. And then you find the equations in time that govern the perturbation. And then you look if the perturbation goes to 0 or not. Okay? And this will be now very similar to what we had with one species that we discussed, the fixed point and so on. But if you do this analytically here, you will have something which is called an eigenvalue problem. And this needs training in linear algebra, and in my experience and the experience of many people is that people that have been trained in biology, sometimes at least they have had calculus, a little bit of calculus. What's a derivative or a simple differential equation and so on. But linear algebra is usually not present. So matrices that you can diagonalize matrices and find eigenvalues and all the stuff that comes with linear algebra, it's not usually present in the training of biologists. So therefore I won't insist on it because that would take us several classes only to do the introduction to linear algebra, okay, which is not what we want to do here. So I will do an explanation of in terms of graphical analysis, okay. So that's the next step, and this takes time because it takes time, because there are 4 fixed points that have to be analyzed, and so what we want to see how this is related to the principle of competitive exclusion, and if the principle of competitive exclusion is actually implied by the equations or not. Okay, and in the next week we will also address the same question, but we will model a resource. Therefore, you have 3, 1, 2, and 3, and they only interact due to the consumption of resource. That's the next week what we will learn about. Okay, so I'm done for today. 5 minutes before the end. Is there any other questions for the next 5 minutes? Or? Yeah, okay, 2 questions. So I don't know who raised their hand before, but okay, you have the mic.
Is this working? Okay, now it's okay. It's because at
Okay.
I'll have to do this. There was one time you said that when alpha or beta is...
Okay, this is intermittence.
It's literally no. When...
I wanted to retire this one, but Natalia said, no, it's working.
Last week, this was the one that wasn't working. But what I wanted to ask is, there was one point you said, when alpha or beta is above 1, it means that species is the dominant one. And when it's below 1, the effect is small or something like that. I wanted to know why.
Okay. So, now first, one thing is suppose alpha and beta are very small, 0.001. Okay, very small, means that the effect of one individual of N2 compared to the effect of one individual of N1, because this term here, N1 over K1, is the intraspecific competition. Okay, it's one individual of N2 has a very small effect compared to the fact that the interspecific competition for N species 1. Okay, so if they are small, very small, then it's easy to see that, you see, you have 10 individuals of the species N2, and then the alpha is 10 to minus 4, then the total effect will be 10 to minus 3 compared to the effect of one individual of the species 1. Okay, so it's negligible in that sense. Okay, so now if they are bigger than 1, say alpha is bigger than 1, you want to compare the effect of both. These are the effects, the relative size of the effects of species 1 on itself, and this is of species 2 on species 1. So say you have one individual of N1 and N2. One individual of N2. Now say alpha is equal to 4. And one individual here, this thing here would be 4. And this one would be 1 if you have only one individual of N1. So comparing the effect of an individual of species 2 to the effect of the individuals of species 1 means that this one has 4 times the effect that this one has on the rates of change of the size of the population. Okay? So then we would call, if alpha and beta are both bigger than 1, you would call this a strong competition. Okay? Because the effects of the competition between species would be bigger than the effects of the intraspecific competition. then here and here. Okay, okay. Okay, so let's go on. So next questions.
Okay. I want to take a look at the same thing you were doing here. What if we do that in one of those fixed points and we have a beta that is very, very small so that the denominator equals to 1 and we have only the numerator, yes, k1 minus alpha k2. How does this behave?
So again, this say you can make sure that this here is small. Okay, it depends also on the value of alpha. If alpha is very big, then it could compensate for beta. But let's say not. Okay, let's say that is almost 1. So therefore, n1 would be at the carrying capacity minus something due to the presence of n2. Okay, so it doesn't attain the carrying capacity. It can attain a level of constant population, but does not attain the carrying capacity because it has something minus here. Okay, and vice versa. And obviously, then it could be the case that K2 is so big that this gets negative. Then there is no consistency at all. Then exclusion. Okay. Yeah? No, you raised your hand there. Yeah, I don't know who raised first. Okay.
Okay, so what you just explained got me thinking about, for example, the competition for a plant resource between a mammal herbivore and herbivore insects. Sure, the effect of one individual of a mammal would be much greater than of one insect, but
yeah, usually
the
you would
population
expect it.
size of an
Yeah.
insect.
So, yeah, sure. If you know, this is you have to see if there is actually real competition in this case. Well, then there are things that have to be more or less. Yeah, obviously, if one individual, but you could think that, for instance, say N1 is a mammal and N2 is an insect. Okay, usually you don't have competition between different things like that. You have usually something very similar species. Okay, but say hypothetically. Okay, so maybe the effect of the insects is very, very big because N2 maybe is very, very big and N1 is not. So that will depend on the case. Okay, so depends.
I liked his question and I didn't really understand the answer because like if there are
Okay,
I don't know, elephants eating leaves and then
yeah, normally between if you have an elephant and you have something herbivore that's whatever, yeah, usually they will have no big overlapping in their resources, but they don't have only one resource usually. Okay, there are many resources, and so the overlap, which will come to the next question, which is what's a niche and so on. We will discuss this maybe tomorrow. So the competition tends to be very weak. Okay, but even if you say it is the effect of one small insect or one herbivore is much less than the effect of a big mammal, okay, then sure, alpha could be small. But maybe there are so many of them that this compound here can be big. So this will depend on more specific situations with the species.
okay, the last question is could more species be added there like an alpha? Could more species be added there like there's an alpha and a beta and a whatever?
Yeah.
And then, because I was thinking of the general, the like the apex species or the
So
more
yeah,
general species, and
yeah, sure.
can that be used to model more than two species? That's the question.
Okay, so you can have other species here. okay? More species, and can build a network of interactions, okay? Then the kind of questions that you answer with this will be more or less more specific. If you have 3 species, then still a lot of things that you can do. But if you have only have a lot of species, what you do is look at limits of. This is already community ecology. Is not so much population ecology. It's in how many species. If you have a network of many species, how does it behave? Is more species stable than less species, or vice versa, and so on? But this is questions that come in when you look for the communities. So I think we have to stop here because it's already running late. Okay, so tomorrow we continue the discussion about lotka Volterra competition.